So we will continue with the next talk. So it will be given by Peter Sarnak online. So he's not here. He's in Princeton. And so I don't know if he listened to me, but
yeah, I can hear.
Please, Peter.
Yeah, thank you very much. I can start, right? Let me apologize for not being there in person for this joint meeting, which has been postponed for too long, but I'm afraid I couldn't make it. So I appreciate that you gave me the opportunity to give this talk online, and probably it's hard to communicate back and forth, but if that doesn't work out, feel free to actually shout out questions. In a normal lecture, enjoy that very much, and I would very encourage that here too. But if not, then just email me after the talk if you have any questions or if you want the slides or references. Okay, so I'm going to talk about prescribing the spectra of locally uniform geometries. And let me start out by saying the style and flavor of this lecture will be in that of the wonderful book Geometry Revealed by Marcel Berger, who, as you all know, was a great geometer and had great students, some of whom are at Grenoble. And this book that from about 2010, 2011, Jacob's Stairway to Higher Geometry, has many of the flavors and notations that I'll be using. However, I'm going to fixate on locally uniform geometries in the simplest case because they are the most challenging. As you'll see, a certain rigidity sets in higher rank and higher dimensions, which I will allude to as we go along. So I'll use this cursor, hopefully, to show you where I'm at. Basically, I'll follow my notes very closely. The upper half plane is the model for many geometries, many interesting geometries. Got the line element, ds squared is dx squared plus dy squared over y squared, gives constant curvature -1. The motion group, I'll use orientation, preserving motions, acts by 2x2 matrices, SL to R, acting projective linearly. ABCD takes Z to AZ plus B over CZ plus D. And if we have a discrete subgroup of this group of motions with finite volume quotient, that's what an orbifold, which will be the topic of this lecture, what we allow here. Then the quotient of the upper half plane, which can be realized as SL to R over its maximal compact. Anyway, the quotient of the upper half plane divided by the discrete group gives me a hyperbolic orbifold. Orbifold means that there may be fixed points in the action, so we may have corners, and then actually, the word locally uniform geometry may be a little exaggerated, but you will allow me to use the orbifolds. In fact, the solution to many of the problems that I'm going to discuss involve orbifolds. Similarly, we have hyperbolic 3-space. These are the two most interesting. 3-space is quite challenging. Same story. We have upper half 3-space, so y positive, z in the complex plane. Again, the line element dy squared plus dz squared over y squared, and the group of motions is the 2x2 complex matrices, which act in a fashion which is a little more complicated than that, so I don't write it down. And we have a discrete subgroup again with finite volume quotient, and we form H3 divided by gamma, and this will be a hyperbolic 3 orbifold. These are the objects that we want to talk about, all of them. And I also want to allow a combinatorial version of this, which is going to just be 3 regular graphs. You could allow any degree of regularity, but 3 regular is actually going to be it's got all the flavors, and there will be features which exploit 3, especially in applications, as I'll explain, that come up. So these pictures are from Marcel's book. These are 3 regular graphs. They are planar. They are on the spheres drawn here. I will make clear when I'm assuming the graphs are planar, when not, but my 3 regular graphs are always connected. I'll assume there are no loops. And by the way, the 3 regular graph can similarly be realized as a quotient of group of motions. In this case, the 2x2 matrices with two adic numbers divided by the maximal compact 2x2 matrices with two adic integers, and then divided by a discrete subgroup with a finite quotient. And this point of view is important in certain constructions. I will not go into them, but you can imagine when the number theory comes in, this is very relevant. All right, that's a setting. And let me just review the notation. So I'll always call the set of all finite connected three regular graphs, I'll just call them the cubic graphs, and the set of finite volume hyperbolic d-dimensional orbifolds, and I'm only going to fixate on d equals 2 and 3, I'll call those hyperbolic D. So those are the sets of those. And the spectra that we want to prescribe in the title of the lecture are the following. So let me make that clear right from the start. So if I take a cubic graph X, it'll have a certain number of vertices and edges. The vertices just simply can be seen to be always even, by the way. And we will use the adjacency matrix to define the spectrum rather than the Laplacian. They're easily related in this regular case. So A applied to a function which is defined on the vertices is you sum over all neighbors W joined to V of f of W. And that's a map on the vector space, a linear map on the functions on the vertices into the complex numbers. Because our graph is symmetric, the operator is symmetric in the standard basis. So the spectrum that we're interested in is a subset of the real line. And in fact, it's very easy to see that the spectrum lies between -3 and 3 because we have three regular graph. And in fact, since the graph's connected, the eigenvalue 3 is the biggest eigenvalue and its multiplicity 1. The constant function is reproduced 3 times itself, and that's very easy to see. It's simple. And the rest of the eigenvalues are ordered in this way. We have n eigenvalues. It turns out that because the characteristic polynomial of this matrix is got integer entries because it's a graph, and because all the eigenvalues again will be real, it turns out that the eigenvalues are totally real algebraic integers. It's not something we use so often, but I will use it at the end decisively. So I point it out now. The Laplacian, because I'm going to talk about the Laplacian on the hyperbolic manifold in a minute, would just be 3i minus a, but it might have been better to always just use Laplacian rather than a. But for the later part of the talk, I want to inspect the inner workings of the spectrum, and then it's better, I think, to use the spectrum of a rather than of the Laplacian. Anyway, they're trivially related. And for a hyperbolic D manifold on L2, so one of these orbifolds, they finite volume, I look at L2, the Hilbert space of L2 functions, then the spectrum of the Laplacian is again real. 0 is a simple eigenvalue. I'm assuming the orbifold's connected as with the graphs. And then the next to biggest eigenvalue, which is an important one for the first half of this lecture, it's called lambda 1, and then they march off to infinity. If the quotient's got a cusp, so the quotient's finite volume in this hyperbolic 2 and 3 manifold orbifold case, if it's got a cusp, it's very easy to see that there's continuous spectrum which starts at a quarter in the case of the hyperbolic plane and at 1 in the case of hyperbolic 3 space. But if the quotient's compact, then these numbers march off to infinity obeying a certain rule. All right, so the main thing about prescribing the spectrum that I want to describe in this lecture is about what values does lambda 1, or more generally, we'll look at probe other parts of the spectrum. So let F be a subset of one of these local uniform geometries, either cubic or hyperbolic D space. And I'll call the base node spectrum or the base node dual. Mark Berger and I introduced something called the automorphic dual some years ago. And this is a variation on that definition. And I'm making this definition because, as you will see, it kind of unifies a number of things that a number of young people have done that I will review in a second, as well as some works that I've been thinking about with some others recently. So the base node spectrum of a subset F of one of these uniform geometries is the set of values assumed by lambda 1. That's what I mean by the base node. lambda 1 of x. And since that will be a very complicated set, I'm going to take the thing that we're going to try to describe. We're trying to describe what the base note spectrum is. With spectrum, you take the closure of this set of real numbers. So that'll be a subset of minus 3, 3 in the 3 regular graph case, and a subset of 0, infinity in the hyperbolic orbifold case. And of course, since I've taken the closure, it may have a discrete part, which I'll denote by the discrete part of this base note spectrum of the subset F, and limit points, which I'll denote by Bass limit of the subset F. So that's just a definition. And in order to understand what we're trying to do here, an important thing is to remember that the universal cover of our object is certainly going to be relevant, at least in some cases. So the universal cover of a 3 regular graph is just a 3 regular tree. The L2 spectrum, the L2, I emphasize L2 there, spectrum of the adjacency operator on a 3 regular tree was computed, I think, first by Keston. Cartier wrote many papers on it as well. Paul Sally computed it in that 2-adic Plancherel version of it. Anyway, the interesting thing is, of course, it's contained in minus 3, 3, but it's smaller. It's minus 2 root 2 to 2 root 2, which is a strict subinterval. I'll give you the exact size of 2 root 2 in a second in a few decimals, up to a few decimals. And the universal cover of the hyperbolic D orbifold is, of course, hyperbolic D space. And its L2 spectrum, I think, was known to many people, Harishchandra, Selberg certainly, Huber, others as well. And it is a quarter infinity in the case that D is 2 in the hyperbolic plane, and 1 infinity in the case of hyperbolic 3 space. So let's start with the graphs where we have a complete understanding thanks to many, many works. I'm afraid I'm going to review a picture here and offer very little in the way of concrete proofs, but I will say a few words about where each thing's coming from. So I'm going to try and understand what lambda 1, this function on the space of all 3 regular graphs, looks like, the closure of that set. So let me run a little baby linear program here, because we're going to do something much more substantial, or report on something much more substantial in a minute. So A is the adjacency matrix, 3 is one of the eigenvalues, and the trace, since there are no loops, the trace of A is 0. So 3 plus lambda 1 plus lambda n minus 1, these n eigenvalues add up to 0. So then trivially, lambda 1, just by this baby linear program, is greater than or equal to minus 3 over n minus 1. The number of vertices, as I told you, of any 3 regular graph is even, and the smallest it can be is 4. So n is greater than or equal to 4, and even so, lambda 1 is greater than or equal to minus 1. So we, without doing anything, see from this constraint that lambda 1, which we're trying to understand what the values it can assume as I go over all 3 regular graphs, is greater than or equal to minus 1. But remarkably, there is a graph which achieves this. And so that's the smallest graph on 4 vertices, 3 regular. What's called K4, it's also the tetrahedron. Its eigenvalues for its adjacency matrix are 3, which was always simple, and minus 1 with multiplicity 3. So that's the smallest value for lambda 1. And I've made a table here as we start looking at graphs with more vertices. I like the ones that I can draw nicely, like these Platonic ones. But anyway, if you look at a table of small graphs and compute the eigenvalues, you'll find that, as we just saw, minus 1 is the smallest value, and then lambda 1 starts to increase. The next is 0, which is not planar for a bipartite graph, K33. Then this graph gives you 1, 1. I want to point out that the number of vertices is not going to dictate the size of this lambda 1, so it sticks at 1 with multiplicity 4. This Peterson graph's got 10 vertices, and it's also still got lambda 1 equal 1. And then we go back to ones which have 8 vertices. Anyway, if you keep going, we can wonder what the closure of the set is. What is the Bass note spectrum of 3 regular graphs? for the purpose of understanding, say, the football, that is my favorite three regular graph, it's got lambda 1 as 2.757, and 2 root 2, which was the edge of the eigenvalue of the universal cover, the three regular trees, 2.824, and so on. All right, so thanks to many people, the theory of expanders, Alon-Bopana, Ramanujan graphs, I'm now going to summarize the answer, which contains all the information that people have proved over the years. So I don't give credit here because there are too many contributors. But the answer is very beautiful. The base note dual, or for the cubic graphs, the base note spectrum consists of -1, as we just saw, 0, 1 with multiplicity 4, and then the numbers march on, and they can be kept by very careful engineering under 2 root 2. There are infinitely many cubic three regular graphs, that is, cubic graphs with lambda 1 less than that magic number 2 root 2. And the limit point set of this base note spectrum is 2 root 2, 3. So that's the entire story. And the part that's kind of new here is that I will explain where it comes from in a second, is that actually there are infinitely many graphs, three regular graphs, which actually give this infinite discrete spectrum. So the discrete part of the base note spectrum of three regular graphs is in fact infinite. On the other hand, if I take the planar subset of cubic graphs, then the numbers lambda 1 must just all the way march up to 3, not monotonically, but they can only accumulate at 3. That is, the discrete spectrum is the interval is a discrete set in -1, 3, open on this side, and the only limit point is 3. So that summarizes what lambda 1 can be for three regular graphs. And if you need to engineer lambda 1, as many people do, this is the story. So let me just say where all of that came from, because I said that's a contribution of many, many people. I mean, it starts with Alon-Bopana, but let me first make a comment about the last part. For planar graphs that lambda 1 goes to 3, I think was known by many people. It certainly follows from computer scientists Lipton and Tarjan. And it's just the statement that planar graphs cannot be expanders. Expanders are graphs which have a gap near 3 for that eigenvalue. And that's just a combinatorial cut theorem. Joel Friedman proved the best inequality we know for lambda 1. So that will imply this discreteness statement. Lambda 1 for a three regular graph is greater than or equal to 2 root 2 minus a constant 100 over log of the number of vertices squared. So as the size of the graph goes to infinity, lambda 1 must start getting close to 2 root 2, at least from the left. That means that the interval -1, which was the smallest possible, 2 root 2, is the discrete part of the base. This interval consists only of discrete part of the base note spectrum. Now, Ramanujan graphs are graphs which have lambda 1 greater than or less than or equal to 2 root 2, but in the definition, it's less than or equal to. So in order to show that the base note spectrum the discrete part is infinite, you actually have to construct graphs, such cubic graphs, which have all that have lambda 1 less than 2 root 2. And this has been done recently by Nina Zubrelina, a student here of mine here in Princeton. She constructs a sequence of graphs using modular forms and the Ramanujan conjectures and the Riemann hypothesis for curves to show that you can make lambda 1 less than 2 root 2 minus, it's very close, but it's less than 2 root 2, 1.3 to the minus the number of vertices in the graph. I should say where this comes from. At some point in the proof that a graph's Ramanujan, you use We's theorem, the Riemann hypothesis for curves over finite fields. Particularly, it's applied to the Jacobian of the modular curve x naught n in this case. And when you do that, you don't learn that's the analog of the Riemann hypothesis for curves. It just says that all the zeros are on the line and a half. It doesn't say that a specific number is not an eigenvalue. But there's a remarkable use of the fact that when Weil gave two proofs of the Riemann hypothesis for curves over finite fields, One, using correspondences, absolute genius, and one, a generalization of Hass's proof, which uses endomorphism rings of the Jacobian, where you're working with abelian varieties. And in that proof, you actually prove that the Frobenius acts semi-simply, which is not known for general, say, in Deligne's proof of the Weil conjectures. You don't know this semi-simple feature. But you do know it there, and then using crystalline cohomology, Coleman and Eidixhoven were able to show that you can keep this multiple. If you have this extreme eigenvalue 2 root 2, you'd have a multiple eigenvalue, and you would be led to a contradiction. So the fact that that this set is infinite is quite subtle. And when I come to orbifolds, this will be not something that we know, but it's something that's quite deep if it's true, and I think it's true. All right, and finally, the fact that any point between 2 root 2 and 3 is an accumulation point of lambda 1 was only proved very recently by Fan Wei and Noga-Alon. And the idea is basically that if you take a random 3 regular graph, we don't know it's Ramanujan, but it's almost Ramanujan, meaning it misses by an epsilon. Anyway, since we're trying to make limit points, that's fine. Take such a random 3 regular graph of very large size. It's known, thanks to H.T. Yao and Wang, that the eigenvectors are then delocalized for this random graph. And because they're delocalized, you can make a very clever argument of changing locally the graph and moving the eigenvalue to any point between 2 root 2 and 3 approximately. And hence, these are all limit points. So that's the story for graphs. And now I want to describe 2 theorems of some young researchers. This happens to be mathematical physicists working in conformal bootstrap. Mazak, who's the person I learned it from, is here at the Institute, and he walked into my office and described this theorem that is part of my motivation for this lecture. I'll call it theorem with a little t, because I think I learned this from somebody who told me Mumford used to use that. In other words, little t means this is essentially proved, but it's not quite written down. And in fact, in the paper, if you go there, they will not claim everything I'm claiming here. And that's because to complete this to a capital T, you would have to use things that are not in their paper. That is not just a conformal bootstrap that I'll explain in a second. Anyway, this is their theorem. It's quite beautiful. The base node spectrum of hyperbolic 2 orbifolds consists of 4 points. And then, so remember, it's going to be a closed subset of 0 infinity, consists of one interval 0 to a number which we don't know exactly, but we know what orbifolds give that number, and 4 guys which lie outside. So it's quite different to what we just saw in the case of the graphs. There's a reason for that, because there's this continuous thing here which has to do with deformations, as you'll see in a second. I'll give you a picture of these 4 in a second. They come from triangle groups. The 237 triangle group is the Hurwitz triangle group, and was shown by Siegel to have the least volume area of all orbifolds. And it's not, maybe it's not surprising that the orbifold of least area has the biggest lambda 1. And the interval there consists of the following. There is a surface, orbifold of genus 0. Its topological type is genus 0, and then it's got type 2, 2, 2, 3, meaning it's generated by elements of order 2, 2, 2, and 3 in the usual classification of surfaces with orbifolds. This is discrete. There's a discrete subgroup with this signature, and it's got a deformation space, a 2-dimensional deformation space, one complex dimension. It's Teichmuller space that is non-trivial. These are all rigid, these 4. And if you look at lambda 1 over this deformation space, when you go to the boundary of this deformation space, lambda 1 will go to 0, and lambda 1 is continuous on this continuous space. And the maximum is this number that you see over there. That's the part that's involving the little t. And so you have this interval, and that's that interval, and then 4 outliers, which are the discrete spectrum. a quite beautiful, I mean, if you told me this was true, I could imagine one way of trying to prove it, but that you would come with such a clean answer proved by one technique, I found quite stunning. All right, these are these orbifolds. That's a Hurwitz orbifold. Here's the eigenvalues. 44 is the biggest one, then 28 going down. Notice that the area is not monotonic. So the smallest area guy gives is the Hurwitz triangle group, but then the next smallest lambda one is not the next smallest area, which you can see here guys of smaller area, but rather the 2, 4, 5 triangle group. Now these groups are reflection groups, and to make them orbifolds, I insisted on having orientation preserving transformations. So you take words of even length in the reflection group, and that would give you orientation preserving, and that's what these orbifolds are. Let me say a word about the proof, because it's quite remarkable. It is, so there's a field called quantum field theory in physics, which part of it is not rigorous, but the proof that I'm indicating, yeah, even with a little t, is all rigorous. And in this bootstrap, they have certain algebras which look a lot like generalizations of the representation theory of SL2R, chiral algebras and Virasoro algebras. And they study various constraints that, so there's a bootstrap constraint equations, and they, what Mazak and his co-workers are experts at is the development of linear program techniques to limit the values of fundamental constants by writing down correlations, positivity conditions, and consistency conditions. And they have really mastered this. And they tried their hand in the case of SL2R over gamma, where gamma is one of these orbifolds. So this linear program runs by writing down these correlations and linear programs, as I said, and then running them on the computer. And what you do is you write down, in this case, 4-point correlation functions involving holomorphic sections. So you look for holomorphic sections on H mod gamma of certain weights. Holomorphic sections you can compute by Riemann-Roch, the dimensions at least. Anyway, you find holomorphic sections, you take you take 4 correlation vectors. So that means holomorphic, holomorphic, anti-holomorphic, anti-holomorphic, and then you expand that real function, you make it positive, something times its conjugate, and you expand it in the entire spectrum of SL2R over gamma, and then the Laplace eigenvalues come in, and you get constraints on lambda 1. So they run this conformal bootstrap, and they get upper bounds for lambda 1, which only depend, they don't know about gamma, they only depend on the dimensions of the holomorphic sections of weight K forms. So they only depend on Riemann-Roch, which singles out these triangle groups. That it gives bounds for lambda 1, which are good to some number of decimal places. Incredibly, for the Hurwitz triangle group, the upper bound that they get is, so they get an upper bound for lambda 1, which is as close as you want to the upper bound. Now, how does anybody know what the eigenvalue of such a thing is? Well, there are numerical computations using the Selberg trace formula. And they find that their upper bound for lambda 1, which never inputs gammas, this group, only this information about the holomorphic sections, is as close as you want to the answer. It seems to saturate, just like I showed you my baby one with the K4 at the very beginning with graphs. In fact, this is very similar to the Cohn-Elkes linear program, which saturates in the sphere packing problem in dimension 8 and 24. And this is no coincidence, because Mazak and 2 of his co-authors give a direct relation between a conformal bootstrap linear program that he's, I said, understood and developed so well, and the Cohn-Elkes, a direct relation, 1-1 correspondence between these linear programs and the Cohn-Elkes linear program. And so much so that he can explain the magic functions of Vyazovska that we are celebrating last week and will continue to celebrate, and Vyazovska et al. to establish the saturation. So the saturation here, there's nothing like the magic function here, but we don't need that for this problem because we just needed to know that number to a few decimal places to isolate that point. But there's something remarkable going on here when these linear programs saturate and recover the information without having the object as it happens here. And as I say, Mazak explains the Vyazovska work as well from this conformal bootstrap linear program theory. Okay, so that's so much so that's a beautiful theorem. That's what the base node spectrum for hyperbolic orbifolds is. And now I'm going to do something which will make this look much more like the graphs. Instead of looking at hyperbolic orbifolds, which was Hype2, I'm going to introduce a new object. It's the object that some of us spend our time looking at, the arithmetic hyperbolic orbifolds. And then I'll even look at something more special. The arithmetic hyperbolic orbifolds are ones which are defined number theoretically, like SL2Z. And there's a whole construction, I don't want to repeat it here, going through quaternion algebras. There's a beautiful paper of André Vey, which tells you how to parameterize all arithmetic hyperbolic orbifolds amongst all of them. So since there was a the arithmetic are certainly countable, they're very special in various ways. There's still a tremendous number of them. And we can ask, what's the base node spectrum of the arithmetic hyperbolic orbifolds? So VAS arithmetic 2. And now we don't have a theorem, but we have some recent progress, and that's why I'm discussing it here. So I'll make this conjecture here, that the arithmetic spectrum consists of a closed interval 0 quarter, much motivated like the graph case, and then an infinite discrete set, which can only accumulate at a quarter. So this is quite different to what happened before, because we don't have any deformation. Arithmetic groups can't be deformed. So we already saw these 4 outliers, those 4 discrete triangle groups. They all happen to be arithmetic, so that's already in the set. And then what I certainly don't know, but I'm conjecturing, that there are infinitely many guys bigger than a quarter. Remember how subtle it was to show that in the graph case. I had to go into the proof, or we had to go into the proof, or Nina had to go into the proof of the Riemann hypothesis and carefully study the semis to avoid. So the point is the eigenvalue of quarters is quite, how do we make these guys have eigenvalue bigger than a quarter, strictly bigger? I'll get back to that in a second. Anyway, the conjecture is that this base node spectrum looks like this for the arithmetic 2, and the discrete part is infinite. And we already know it's got many points, but the conjecture is there are infinitely many there. And that every point between 0 quarter is an accumulation point. So this is a conjecture, but we know quite a bit towards it now. And there's a recent breakthrough. So let me explain that. So firstly, that the base node spectrum is discrete in a quarter infinity follows from the theorem of Borel and Prasad, which asserts that the number of arithmetic hyperbolic orbifolds of area less than a fixed number C is finite. So the only way I could have an infinite sequence accumulating somewhere is if the volume, or the area in this case, of the surface started to increase. But then there's a well-known application of the trace formula by Heinz Huber, which shows that lambda 1 lim sup must be less than or equal to a quarter. That's similar to this Alon Bopana that I alluded to before. And hence, the only possible accumulation point is, the first accumulation point possible is a quarter. So the spectrum is discrete in a quarter infinity. What I don't know is that it's infinite. A recent breakthrough by Hyde and Maggie, quite remarkable, gives that the base node, the limit, constructs limit points of arithmetic orbifolds. What they show is that if you have any arithmetic cusp surface, because the fundamental group has to be free. So you take a group, an arithmetic group in SL2R, which is for which the pi1 is free, and it's got some spectrum, and they show that the smallest eigenvalue of y, if it's less than or equal to a quarter, then it's actually in fact a limit point of eigenvalues as you make bigger, and you can construct a sequence, infinite sequence, with that as a limit point. And as a consequence, they have something fundamentally new, that the arithmetic base note spectrum contains a quarter. That's their breakthrough. That 0 is a limit point of arithmetic quotients was already observed by Selberg using cyclic covers many, many years ago. What Hyde and Maggiorelli show is that if you take a random n-sheeted cover of such a y, then the smallest eigenvalue, lambda1, of this n-sheeted cover, it must be at least, can't be any smaller than lambda1 of y, but it's going to be, the lim inf is going to be equal to the minimum of lambda1 y and a quarter. So that's how you get a quarter in as the limits here. Along the way, they solved a long-standing question of Peter Boozer, that they exist, do they exist hyperbolic, compact hyperbolic surfaces of arbitrary genus with lambda1 greater than or equal to a quarter minus epsilon for every epsilon? And this constructs ones with cusps, and then they use a theorem of Berger, Boozer, and Dojek to remove the cusps and resolve this problem. This is really a beautiful argument using random covers and using ideas of Bodenave and others. For the random surface of genus G, you might ask whether lambda1 can be shown to be bigger than a quarter minus epsilon by taking a random surface relative to another measure called the Weil-Petersen measure on the moduli space of curves of hyperbolic surfaces of genus G, compact, smooth. And Mirzakhani, one of her lovely works, showed that, in fact, you can find a positive number. I can't remember if she wrote down a number, but anyway, there's a positive number such that for the random Weil-Petersen surface of arbitrary large G, lambda1 is not going to 0. It's bigger than epsilon naught. And this was recently improved by two groups, Lipnowski and Wright, and Wu and Xu, to give the epsilon naught equal to 3/16. But right now, this method is stuck at 3/16 and can't get up to a quarter, and that is why this so far is doing better. The random cover is easier to study than the random Weil-Petersen metric. I don't go into one. All right, the holy grail of the subject, where I come from, is now let's restrict not just arithmetic, but also congruence. These are the ones that come from number theory, congruent surfaces. They are special arithmetic. So SL2Z would be such a thing, and any congruent subgroup, that is a subgroup defined by congruence conditions of SL2Z, would be such, and they can be defined generally over number fields. And the holy grail is the famous Selberg conjecture that the base note eigenvalue of a congruence surface is greater than or equal to a quarter. So in that case, the base note spectrum for congruence to, so this is Selberg's conjecture, would be that it can only be in the interval to the right of a quarter. If you finite volume, then a quarter is the base eigenvalue under this conjecture, and there are many of those, so that would a quarter would happen very, very often. I say Selberg plus epsilon, I'm throwing in the epsilon, I highlighted why I like this epsilon, is that there should be, the base note spectrum should contain also infinitely many guys for which lambda1 is bigger than a quarter, bigger. This looks very hard to prove, but I have no doubt it's true, so I call that plus epsilon. And the limit points are, of course, only a quarter. Okay, what do we know towards this using the full force of Langlands and functoriality and techniques related to that is due to Kim and myself. We don't know this conjecture, but we are quite close. We have a lower bound of 2.38, which is not that far from a quarter, but we've milked this to its limit. I should say that we worked over our congruence groups were over Q, and the extension of our work to number fields was by no means easy. It required a fundamental new idea, and so that's due to Blomer and Bromley. All right, let's turn to hyperbolic 3 manifolds. So now I'll review for you some remarkable things about the structure of volumes of hyperbolic 3 manifolds, which will play a role into this. Anyway, the conjecture here, very different to hyperbolic 2 orbifolds. For hyperbolic 3 orbifolds, the conjecture is again that you can produce limit points in 0, 1, and infinitely many above 1, and that probably it is known which hyperbolic 3 orbifold, it's this one over here, has a smallest volume. This is just a guess that it would have the biggest lambda 1. And the fact that there would be infinitely many here is a very strong statement, just like it was for the arithmetic case that I was describing before. So this is a conjecture, and let me tell you where it's coming from, why the base node spectrum, at least this should be structured like this, and what we know. So we learned from Jorgensen and Thurston that the hyperbolic 3 orbifolds are well ordered by volume. They actually have limit points, but they're well ordered. That's quite unusual. And the limit points of these volumes correspond to cusped such hyperbolic 3 manifolds with a sequence of yj's converging to y by Dane drilling, which have a quite strong convergence of these, say, compact 3 orbifolds to this cusped 3 orbifold. Now, works of Colgois and Coitat, coupled with Chauvel and Dojek, show that in under this convergence, lambda 1 of yj must converge to lambda 1 of y. And since y has got a cusp, lambda 1 of y is less than or equal to 1. So this means that the lim sup, so that means that we can't make an accumulation point in this process of, in the limit points of the Jorgensen-Thurston setting, we cannot make an accumulation point which is bigger than 1. Moreover, so the only way we can try and make an accumulation point which is bigger than 1 is if we at the same we allow also the volume to go to infinity. But then the Huber argument comes in, and coupled that with those two, we learn, and that's what I'm pointing out here, that the base node spectrum for hyperbolic 3 is discrete in 1 infinity. And that's what we know. And using that there are some hyperbolic cusp 3 manifolds for which lambda 1 is small ones, which you can actually even numerically compute lambda 1's greater than or equal to 1. You have something similar to what we had in the case of hyperbolic 2 orbifolds, that the base node spectrum, the limit points contain 0, again, because of abelian covers, which you can produce. That's related to covers with positive Betti number. And the case that I've just explained here, well, 1 is a limit point. So that's what we know. I think it's a very interesting problem to compute, as Mazak did, or at least understand the beginning part here of the 3 manifolds which have the biggest lambda, 3 orbifolds which have the biggest lambda 1. All right, I have taken 3/4 of my lecture on this lambda 1. I want to now talk about prescribing the spectrum, gaps in the spectrum, or understanding this prescribing the spectrum in other parts of the spectrum, not just at the bottom. In fact, this is the work that I want to describe myself with 2 young researchers, who I'll mention who they are in a minute. In the setting of cubic graphs, it was Alicia Koller, who's an applied physicist, who came and asked me questions. They were building these 3 regular graphs in that laboratory, and they need to know where they can make gaps in tight binding models for Hamiltonians. These problems come up in carbon clusters, in Huckel's stability of fullerenes. And I want to show you that there is an amazingly rich theory. But before I turn to that, let me make 3 definitions, and then just stick one more moment with the hyperbolic case, because we know so little there that I want to popularize these problems. So given any family F as we had above, instead of looking just at lambda 1, I'll say that U contained in 0 infinity is a gap set for F if there's an infinite sequence of members of F for which the spectrum of these members does not meet U. So you're trying to prescribe an infinite, are there infinitely many members in the set which have no eigenvalues in U? So if that's the case, U an non-empty open set, I'll say U is a gap set. The corresponding complement to that is a subset K of 0 infinity is F spectral if there's an infinite set in F for which the spectrum of all these guys is contained in K. So it's just a complement of that. It's just, I want to formulate some theorems in a minute. And perhaps the most important and interesting question, which is what engineers want, is if you have a point in the spectrum, can it be F gapped? So can you find a neighborhood in the point so that there are infinitely many X's in F which have no eigenvalues in U? That's the kind of thing that an engineer who's building networks, in her case, waveguides, Alicia's case, wants to know. So just to explain this in a hyperbolic case, so suppose I have arithmetic 2, we just mentioned the Hyde-Magee theorem, says that 0.25, the open interval, is a gap set. They essentially proved that. They only proved it quarter minus epsilon for every epsilon. But suppose they proved that, that would be a gap set. That's just to illustrate the definition of a gap set. And now a question which I don't know the answer. In the graph case, I'm going to give you an answer. It's extremely rich. But for which C in a quarter infinity, so this shows that you can gap points between 0 and a quarter. Hyde and Magee do that. For which C in a quarter infinity, as we saw, a quarter is a very important number in this game, is there a neighborhood U of C such that an infinite sequence with no eigenvalues there? Can you gap every point in a quarter infinity? I don't even know what to conjecture here. It's a question. I want to remind people, because this is an amazing piece of work of Scott Wolpert that is not recognized perhaps as much as it should be, and it's got an amazing theorem. In his series of papers in which he tackled the conjecture of Ralph Phillips and myself, he proved the following theorem, that for a fixed moduli space MG of compact surfaces of genus G with curvature, with a hyperbolic metric, and given any C in 0 infinity, there is a surface in MG for which C is not an eigenvalue. This might seem trivial, you just jiggle the surface, but you have only finitely many parameters to jiggle. And he proved this as a consequence of his series of, it's probably 600 pages altogether. So it would be nice if there were an easy proof of what seems to be a very basic fact. Anyway, this will get you started on this, because I want the volumes to go to infinity. And one more thing before I state what we know in the graph case. There is great rigidity in the subject, and this is where I'll mention something in higher rank also. So if you take the congruence orbifold or the congruence 3 manifold case, and you ask whether you can gap a point in a quarter infinity or 1 infinity, the answer is no. You cannot make any gaps in that. So Selberg says you should never have eigenvalues in a 0 and a quarter. That's an amazingly strong statement. And this says no other point can be gapped with congruent surfaces. And this follows from a very beautiful theorem of Freitschig, recent theorem, which says that if you have a sequence of x's in either hyperbolic 2 or hyperbolic 3, which are congruents, then this sequence of surfaces must Binyamini-Schramm converge to the underlying hyperbolic space. Binyamini-Schramm convergence means that it starts to look like the universal cover. Not exactly, but if you take a typical point, then it will look like the universal cover in bigger and bigger neighborhoods. So that it may not look exactly like the universal cover, but it probabilistically looks like universal cover. And if that happens, then the spectrum must become dense in the interval a quarter infinity or 1 infinity in dimension 2 and 3. So this is a remarkable rigidity. It says you can't make gaps with congruent surfaces. And there's a dramatic statement by 7 authors, Aubert, Bergeron. They call themselves the 7 samurai. I once heard them refer to themselves as. They showed that in higher rank, if you have local uniform geometries like this, and the volume goes to infinity, then you have no option. You have to Binyamini-Schramm converge to the universal cover. So you can't make gaps outside, inside the tempered spectrum, as we would say. Let me skip the next because I'm running out of time. All right, so I want to describe in the next 5 minutes what we know for cubic graphs, I returned to the graph case for which the base note was completely understood. And now we want to understand some other gap sets. This is joint work with Alicia Collar, who, as I said, is a young applied physicist at Maryland, and Fan Wei, who's a young combinatorist at Princeton. So we've seen that 2√2,3 is a maximal gap set interval in the case for cubic graphs. That was the Ramanujan graph feature. How about a gap at the bottom? This is the reason I didn't write it as a Laplacian to begin with. So there's a nice observation that if you have an induced subgraph of a graph X and you look at the adjacency matrix, then just by min-max characterization of eigenvalues of a symmetric matrix, the minimum eigenvalue of X is less than or equal to the minimum eigenvalue of H. And so if you want to know whether lambda min is bigger, can be bigger than -2, the smallest eigenvalue, which you saw was -1 for the complete graph, but maybe I want to make the smallest eigenvalue bigger than -2. I'm now looking at the gap between -3 near the bottom. Well, if that's going to happen, then there are many small graphs which have their smallest eigenvalue less than -2. In fact, you just look at any kind of small graph, it'll have that property. They will not allow to be minors because they can't be induced subgraphs of such an X. So they're forbidden minors. And there's a structure theory, Seymour Robertson theorem, which says under such circumstances, when you have forbidden minors, you should be able to characterize graphs. And in this case, there's a beautiful work from 1975 of Cameron, Gothel, Seidel, and Schult called Line Graphs, Root Systems, and Elliptic Geometry. And they classify all finite graphs connected for which lambda min is greater than or equal to -2. And we're not allowing, because we're looking at induced subgraphs, we're not assuming things are regular here. It's an amazing classification. It involves line graphs and cocktail graphs. Anyway, if you apply their theorem and do a little bit of work, as Alicia and I did, then you have the following remarkable fact, that if X is a cubic large graph, and then its smallest eigenvalue, now I'm talking about the smallest eigenvalue, is less than or equal to -2, must be, so it can't be bigger than -2, so the smallest eigenvalue must be less than or equal to -2, and it can be equal with infinitely many, and it's equal if and only if something amazing happens. X is T of Y, where T is the map from cubic graphs to cubic graphs, which is obtained by inserting at each vertex an equilateral triangle like that, a triangle like that, which takes a cubic graph to another cubic graph, which is 3 times bigger. And you can make a simple computation that the spectrum of T of X is the following. It's the inverse image of the spectrum of X together with 0 with multiplicity n over 2 and -2. So this is how you get -2 in the eigenvalue with multiplicity n over 2, where F is this nonlinear map of the interval -3 to 3 of the line to the line quadratic map. So if you want to understand what the spectra after iterating with T looks like, you would have to study the dynamics of F, and we do. And this has a Julia set, which plays a big role in this. So in particular, you learn from this theorem of Gothels and Cameron, as we apply it, that -3, -2 is a maximal gap set for maximal planar gap set, an interval for 3 regular graphs. So we've answered the question at the top and the bottom. And here's our one of our main theorems. This is Collar and myself. So what kind of gap sets can you construct in the spectrum between -3 and 3 for 3 regular graphs? And we have a number of statements. The first 2 are constraints on what you can do. You can't just go around making gaps willy-nilly. So if K is a cubic spectral set, that means, remember that there's an infinite sequence of cubic graphs. K is a closed set in this case, in -3 and 3. K is a cubic spectral set, then the capacity or the transfinite diameter of K must be at least 1. I'll explain to you why that is in a second. That's a very strong potential theoretic constraint. purely combinatorial theorem that we were able to prove is a gap interval. So if I have an interval which is free of eigenvalues for an infinite sequence of 3 regular graphs, it can have length at most 2. And perhaps the most important thing we prove, and this is what she wanted to know, is that every point in -3, 3 can be gapped with planar cubic graphs. I should say for engineers, and in what she does with these waveguide and wires, it's natural that you have cubic graphs and that they be planar. So one can gap every point. Remember in the hyperbolic surface case, I said I don't know even what to expect. There are, and so I'm now complementing these two statements. There are cubic planar graphs which have capacity 1, so that you can get down to this minimal capacity. In fact, the Julia set of that map F does the job. And we have that -1, 1 and -2, 0. These have length 2 are maximal gap sets. They're maximal according to that theorem, but we can actually make even the first one planar. Just a word here that the reason for A about the capacity or the transfinite diameters is this beautiful theorem of Facketer, which asserts that if you have a compact subset of the plane, and has the property that it contains, and you look at all algebraic integers which lie in K, and all their Galois conjugates also lie in K, algebraic integers and all their conjugates lie in K, then the capacity of K must be at least 1. So that's the workhorse to prove A. So this is where we use that property that the eigenvalues of a 3 regular graph at algebraic integers totally real. And to end, I'm very in this kind of problem, you're very interested in what constraints you put on the graphs so as to limit, so as to not to be able to gap anymore. And for that purpose, let me define Fk to be the set of planar cubic graphs with at most k edges per face in its planar realization. There's only one realization. The duals of such graphs are triangulations of S2 in which the vertices have degree at most k. There's a very interesting case here. F6 corresponds to what Thurston calls triangulations or convex or non-negative curvature. In fact, he's got an amazing theorem that I only learned recently, that he can parameterize these triangulations, F6, in terms of orbits of an arithmetic group in SU9 1 of an integer vector. Anyway, the subset of F6, which consists of planar cubic graphs with 6 and 5 sides only, not just less than or equal to 6, are called fullerenes. They are things like this that chemists have been interested in for years. There's the soccer ball, there's the carbon, these are called carbon clusters. So as you can see, if you only have 6 and 5 sides and you planar, there are going to only be 12, exactly 12 pentagons, and all the others are hexagons, but they have all these shapes. And the question is what gaps, and they're very interested in what gaps you can create in the spectrum of the adjacency matrix. So, and this is the final slide. This is a theorem that we're still writing up, Koller, myself, and Fan Wei. So this is the question of at what points does this prescribing the spectrum of these 3 regular graphs rigidify? If you have at least 64, this is not sharp, but it's what we've managed so far. So we have improved our result, which is that you can gap any point with planar graphs. You can actually gap any points in -3 and 3, every point, with planar graphs with at most 64 sides per face. That requires a much more complicated dynamical system than the F that you saw there, that simple quadratic map. And as far as the convex ones, F6, so we believe this is true all the way down to 7, but at F6 there's a dramatic change. So for the convex ones, the ones which have only 6 sides or less per face, you can only gap points but in -1, 1, no other points, and this is the unique maximal gap interval. So we understand completely the gap in question for F6. And for fullerenes, we understand it as well. It's going to be a subset of this. One can gap any point between minus A and A, where A is 0.382, slightly smaller than 1, a lot smaller than 1, except for a miracle point B, which you can't gap. A and B are algebraic integers, algebraic numbers, sorry, that come out of the proof. So I don't have time to explain, but we'll be posting this paper this summer, I hope. And let me thank you again for allowing me to speak here. I hope you're still there. I haven't heard a peep from anyone. And have a great conference. Thank you.
Thank you, Peter. So I will ask in the amphitheater if there are some questions, comments. Yes, there is one, so I have to walk. I like sports.
You know, with these Zooms, I got a little worried that maybe I've been talking to myself for an hour. Maybe I got cut off in the middle. You guys are too polite.
So thanks a lot for the nice talk. I was wondering, in your conjectures on the base sets, the base set that you conjecture for Hype 3,
yep,
is much more similar than the one for arithmetic 2 than the one for Hype 2.
Correct.
Is there a heuristic reason for this discrepancy?
Yes, there's a very good reason. The reason is, there are two reasons. Firstly, the reason that Hype 2 and that Mazak and co got this answer to have this interval is that in Hype 2, so in a hyperbolic space, the space of discrete groups with finite volume quotient need not be rigid. There's these moduli spaces, deformation spaces of Riemann surfaces and of these orbifolds. And that's the reason that he's avoiding, you don't see the number quarters. So there's this one Teichmuller space that covers this whole interval, and all the deep action is happening down here, which, since if you just ask for the closure, you miss it. On the other hand, the minute you go to hyperbolic 3 space, you're locally rigid, that's Selberg, and you globally rigid, that's Mostow, and then, as I explained, so there are only countably many such things, so already you can't get an interval. And then the fact that these well-ordered, so we're talking about Hype 3, the fact that Thurston and Jorgensen showed that the only way you can make an infinite sequence of hyperbolic 3 manifolds without making the volume gate large is you have to limit in one of these cusp guys with a drilling. And when you do that drilling, you have to go down to 1, is what I was trying to explain. So that is a very basic difference, and it's why it looks so similar. I hope that answers that, yeah. What's very suspicious here, that I put the question mark, is I have no evidence that this, I don't know what the first eigenvalue is for this Marshall-Martin tetrahedral reflection group, but it's got the smallest volume, so it's quite a natural guess there. And just to be clear, what's really, I'm sure true, but probably quite hard to prove, at least for me or for what we know today, is that there are infinitely many above 1 here. So anyway, I would say the answer to your question is deformations.
Thank you for the question and the answer. So, okay, now another question.
What if you just look at regular actions without fixed points? So you just get manifolds instead of orbifolds. Right,
that's a good question. So in the actual extremal, so in Mazak's theorem, if you these are orbifolds, and these are all orbifolds, then you would be facing like, what's the biggest eigenvalue on the genus 2, say, smooth hyperbolic orbifolds. And there's a conjecture what that would be, and you would get an interval for that guy. So you would have a different kind of problem. To make it jive with this phenomenon, we would then have to make the genus start to go to infinity, and then the story, I think, would become very similar. So in other words, this picture is always going to, once you get away from the, if we get a hyperbolic 3 space or put anything which makes the set countable, then I believe the answer is always going to be this kind of picture that you keep on seeing, infinitely many, and this kind of picture over there with a continuum in a 0 quarter, but with different, as you make more restrictions, these numbers will get sparser, but I believe still always infinite. But that has not been studied. And the remarkable thing, just let me go back to this bootstrap. These guys came out of the bootstrap, and by far the most interesting out of the bootstrap is that you're saturating at this number. That requires an orbifold. So I would say the conformal bootstrap does not do very well on the other ones. They discuss it in their paper, and the numbers are not good. I should say that's very similar when the Cohen-Elkies, if you run the Cohen-Elkies linear program in dimension 3, you want to get Hale's theorem this way, it's very bad. It only works in dimension 2, 8, and 24, where it saturates. This is something that really needs to be understood, especially now that it's connected with this conformal bootstrap linear program. So we've definitely engineered the orbifold here, or Mazak has, to get that number 44.
Thank you. Yeah, you have a comment?
If you apply your construction to universal type Miller space, what kind of spectra do you get? Have you looked at that?
So what's universal type Miller space?
Well, it's this super type Miller space for which all the others can be embedded in. All the type Miller spaces can be embedded in universal type Miller space. It's essentially the diffeomorphism of S2 over the conformal group of S2.
Ah, don't know. I'm not familiar with that space. But if it's a union of all the others, then of course these.
It's not the union quite.
Yeah. Okay. Then sorry. Then I need to. Who's talking?
My name's Arthur Fisher.
Okay, so maybe we can email and you can, I'll think about it. Interesting question. Thanks.
Thank you. Some other question? No, I think there are no more questions. So I would like to thank again Peter, because it's very early in the morning.
It's not so early anymore.
For me, yes. Thank you very much.
Thank you for allowing me to speak, and have a great conference.